Okay. Let's see. To give you more examples to play with, um, here's another one. I hope you will try to work it out during this tutorial. So consider a car of mass m accelerating at constant rate a. Its center of mass is midway between the front wheels and rear wheels, as well as at is at a distance h above the ground. The wheels are at a distance L apart. So you can consider it like a rectangular box, right? What is the minimum acceleration A of the car so that the front wheels just begin to lift off the ground? If the car decelerates at rate G, what is the normal force on the front wheels and on the rear wheels? Okay. Now, obviously, it is you're advised to use the non-inertial frame, right, to work out the details. So to start with, you will draw the force diagram within the non-inertial frame. Why should we start analyzing this problem using the non-inertial frame? The answer is that in the non-inertial frame, it becomes a static problem, right? A static problem. when you study mechanics in high school, all of you remember that, all of you should remember that you start with static problems and then dynamics problem, right? So static problems should be easier. Now one may wonder uh, why, why are we required to find the minimum acceleration instead of maximum? When the front wheels just begin to lift off the ground, the normal reaction at the front wheel will become zero, right? Okay, so I give you some hints. I draw the force diagram. F1 and F2 are the frictions, and MA is the fictitious force. Mg is the weight of the car. Since this is a static problem, so the rotation, it is in rotational equilibrium, and also in translational equilibrium. Does it help? If it is in rotational equilibrium, what do you need to do? Okay. All right. Mm. Okay. Okay. Right. Okay. So that's the answer. Since it is in rotational equilibrium, so we take the talk about the back wheels at the point of contact with the road. Okay. So this force, the fictitious force, has this moment, HMA. The normal reaction at the point of the front wheel, at the point of contact near the, at the front wheel, is equal to L times N2. And the moment due to the weight is minus half L mg, right? So we can determine N2. That is equal to 1/2 mg minus h over L ma. For N2 equal to 0, we obtain A equal to L over 2h times A. All right. So that is the minimum acceleration. All right. Now part 2. Part 2, if the car decelerates at rate g, what is the normal force on the front wheels and on the rear wheels? No, you just treat part one and part two separately. So you can just say, if A is equal to minus G, what happened? If A equal to minus G, what happened? If A equal to minus G, what happens? Okay, here we just pop in the value A equal to minus G into the equation here, and you get N2. Since N1 plus N2 equal to mg, according to the force diagram here, so we can get N1 as well. And you can see that N2 is larger than N1 if it decelerates. All right. Now, if I ask you to do this problem in the left frame, what will happen? In the inertial frame. Inertial frame. Why? So it's moving. The point of contact is changing all the time. So it's hard to imagine that you can do that. Am I right? When you are using the non-inertial frame, then you have a point of contact, and you can take moment about it. Okay, let us go back to another question that we encountered last time. Oh, not this one. Okay, last time we worked on this problem. A cylinder of mass m and radius r rolls without slipping on a board, right? Which is accelerated at the rate a. I ask you to find the acceleration of the cylinder. So we go into the uniformly accelerating frame and treat it something treated in the same way as a cylinder rolling without slipping in the presence of a fictitious force. Am I right? Okay. Now, I add one more complication to it. Actually, the board, the plank, is inside an elevator, which is moving upward with a uniform acceleration, g bar. Okay, g bar. What is the acceleration of the cylinder observed in the left frame? Can you follow me? The plank is actually accelerating upward as well. Okay, this is the original problem. Now we add one more complication to it. This board is going upward with a uniform acceleration, g bar. Mm-hmm. Okay. Yep. Because inside the cylinder, I mean inside the elevator, you can see the cylinder is rolling without slipping. Am I right? You don't see any vertical acceleration at all. Now, there's another one. You will encounter, let me warn you, in the final exam, you will encounter a lot of short questions. For example, okay, you have a mass sliding down the inclined plane. Okay, you all know how to do it. Now this time, the first modification is actually inside the elevator. This elevator is going up with a uniform acceleration g bar. What will happen? What is the time for it to go from top to the bottom. Okay. When it is when T bar equals 0, what is the time for this mass going down to the bottom? If you have if the T bar is positive, what happens? If T bar is negative, what will happen? All right. The second part, actually, this is a moving board or inside a bus. And this bus is accelerating with A. Accelerating with the rate A. How does it affect the time for this mass to go to the bottom of the time frame? If A is positive, if A is negative, what is the result? Okay. These are not questions. That's it. So you keep in mind that don't try to work out a lot of details. A lot of calculations you cannot. Because this is a very simple problem you have in the things you were in high school. Okay, can you follow? All right, let us take 5 minutes break and then we can resume. Okay, 5 minutes break. I forgot to resume. Okay, let me repeat. Now this is a new problem concerning the rotating frame. And there is a pendulum which is rigidly fixed to an axle held by 2 supports so that it can swing only in a plane perpendicular to the axle. All right, you can treat it as a pendulum clock at home. This rod is weightless, but it is rigid, so it just swings back and forth. If you are sitting on the rotating disc, you only see the pendulum swinging back and forth. All right. Now, in the left frame, when you go into the when you are in the left frame, you see that the pendulum is actually rotating at the same time. It is oscillating back and forth. Okay. Now, for small amplitude motion, find the frequency of the pendulum. Obviously, I would advise you to use the non-inertial frame to work out the problems, work out the solutions. So I give you a hint. You don't have to worry about the Coriolis force, right? Coriolis force 係 tangential 嘅，因為佢而家係 fixed 咗嘅 rigidly fixed to a plane。 Any idea? Okay, here's the answer. All right. Now, in the rotating frame, there's a radial force pointing outward, the centrifugal force, right? Because it is rotating about the z-axis. The top equation about the pivot point A here, about this point, is given by this equation, minus mgl sine theta plus the centrifugal force times L cosine theta, right? This is the net torque. On the right-hand side is the angular acceleration, okay, ml squared theta double dot. So the theta double dot is given by this expression. When theta is very small, sine theta is can be approximated by theta. So we have a very nice expression. Theta double dot is equal to omega, capital omega square minus g over L times theta. So if the rotational frequency, frequency is less than the natural frequency of the pendulum, then this is the answer, right? And this omega, small omega, is the net or the effective frequency, natural frequency of this pendulum, all right? If the capital omega is larger than the natural frequency of the pendulum, then the motion is not harmonic anymore, right? Now you can see that when you go into the rotating frame, the whole analysis is very simple. If you don't believe it, then I advise you to go to the inertial frame and work out the details. Okay. Now, of course, I will add one more thing to it. If this axial is going upward, is inside, the whole merry-go-round is inside a big elevator, going upward with a uniform acceleration, what will happen? The elevator is going upward. Yes, right? So you can see the effects of uniform acceleration and also the rotation. All right. So I think you start to getting a hold of what's going on. All right. So what's next? Now, let me modify this problem a little bit again. Remember this last time? Now, instead of letting the bead move smoothly or slide smoothly along the rod, okay? Let the bead slide smoothly along the rod. We attach a spring of natural spring constant K to this bead. The natural length of the spring is 0. Okay, so what will happen? What will happen? obviously, in the radial direction, we have an extra force, am I right? In addition to the centrifugal force, we have a restoring force due to the spring. Okay? Get it? Okay, if I add a spring to this beam, the spring constant is K, the unstretched length is 0. What will happen? What we need to do is to add the restoring force to the fictitious force here. Okay, and that's it. Obviously, the restoring force is proportional to R, right? So basically, you will see that the equation remains the same form because the restoring force is proportional to R. Okay. Now another complication. Another complication. If we add, if this instrument is placed inside an elevator which is going upward with a uniform acceleration, what will happen? Will the results be affected? Will the results be affected? If this instrument is inside an elevator, the setup is exactly the same. Right. Nothing, no effect at all. So this is good for a short question, right? If you don't understand the problem, then you have to work out the details and you spend a lot of time. Okay, that's good. Now, there's another example. Because of the Coriolis force, falling objects on the Earth are deflected horizontally. Because the Coriolis force is a tangential force. For instance, a mass dropped from a tower lands to the east of a plumb line from the release point. Okay? Now calculate the deflection for mass m dropped from a tower of height h at the equator. Okay, I make it easier. Equator. Just don't look at your notes and try to work it out. I mean, don't look at the answers. You can look at the previous notes about Coriolis force and also centrifugal force. Earth, okay, the Earth's surface. So it is rotating up about this axis. 好明顯咩？當你畫個 force diagram 喺呢個 particle 上邊，即係 force diagram of this particle，有乜嘢 radial force 啊 ？gravitational， 仲有咧 centrifugal force，right？ 咁係 tangential force 咧 ，Coriolis force，right？So you have all the forces already. So you can have two equations, all right? So in the coordinate fixed to the Earth, the apparent force on M is given by here, all right? Gravitational force, Coriolis force, and centrifugal force, right? Now, whose component along the theta axis is minus 2m r dot theta? And we know the v rotation in the rotating frame, the v is equal to r dot r hat plus r theta dot theta hat, all right? So the FR, performing all these a little bit more complicated vector calculus or vector algebra, we can find the magnitude of the radial force is equal to minus mg plus 2m omega theta dot r plus m omega square r, right? The centrifugal force. Then in the radial direction, we have this, okay? Radial direction. And tangential direction, we have this. We have the Coriolis force on the right hand side. Now, since theta dot is much less than the capital omega, then we can omit the terms like mr theta dot square, 2m omega r dot theta dot, and also this term, so that the equation of motion is reduced to this form, if this is true, okay? Now, so the r double dot is simply given by this, the gravitation force, gravitational acceleration, and also this centrifugal acceleration. And this is the tangential component. R theta double dot is simply given by the Coriolis acceleration. All right. Okay. So you can see that basically what you need to do is to redefine the composite term as the so-called effective acceleration due to gravity. Okay, get it? All right, so that's how you tackle this. Now, if we all know that life is tough. If it does not happen at an equator, if it happens at a latitude lambda, what will happen? Say, for example, Hong Kong. Hong Kong is not at the equator. What will happen? What will happen? And we will repeat the same calculations. Am I right? But remember this time, it's good to use vectors instead of components. Because if you keep using components, then it will complicate the problems. All right, how to define radial components, tangential components, all these. So if you keep using the vectors, it will simplify the problem. Okay? Get it? All right. Now, this part is actually related to the Foucault pendulum. And obviously, I will give this exercise, not as an example, as a question in the next problem set, so that you can explore it by yourself. Okay? Yes. Example 2.佢跟住個地球轉㗎嘛？佢原本有㗎嘛？係啊，嚇！你唔記得咗啦？你諗下你喺即係你喺架巴士上邊，你揸住個嘢，佢其實都有 initial 㗎，即係你就算放咗手，佢其實都有 initial motion 㗎嘛，係咪 ？Okay. Okay, I think I'll stop here today, and remember to download your problem set number 6 tomorrow. Okay. All right. Thank you. Yeah. Yeah. Okay.